Voltorb Flip is one of the most notorious Pokemon minigames, and for good reason. The game's difficulty and the extortionate prices of the game corner force players to spend hours grinding away just to get one Thunderbolt or a couple of Pokemon. To top it all off, the game isn't even possible to be solved every time. This is why I was stupid enough to try and make an automatic solving program. Voltorb Flip is like a 5x5 minesweeper, with the numbers at the edges showing the sum total of each row and column. It also tells you how many Voltorbs, which are the bombs, are in each row and column. To go to the next level, you have to flip over all the 2 and 3 tiles without turning over a Voltorb. As the program needs to see what's on the screen to react to it, we can write a function to take a screenshot and return it as an array. Then every time we need to look at the screen, we can call this function. But how do we recognize the digits in the image? It's obvious to us as humans, but the program just sees a bunch of numbers with no link between them. If only there was some way of training a program to recognize them. I know you're all yelling at me, Jamie, just train a neural network to recognize the digits, but no. Actually, that's not a bad idea, but it's too late now. Template matching is the way forwards. I cut out images of each of the digits and gave them a grey background. The function then takes slices of the screen for each digit location and compares them to each of the template images. If the comparison's over a 95% match, the function returns that digit. We also need to be able to recognise if a flip tile is a Voltorb, 1, 2 or 3. This could also be done with template matching, however there's a faster way. We can first check to see if a Voltorb has been uncovered by looking at the centre pixel and seeing if it's the same colour red as a Voltorb. If it's not, we can look at this specific pixel on a tile to work out the number, as it'll be a different colour if it's a 1, 2 or 3. Check it out, the program stores all the edge numbers and recognises what number is on a tile when we flip it over. As for clicking on tiles, that's easy, as long as we don't end up in a situation like this. That's all working, so let's move on to automating all the text boxes and menu navigation. This is actually pretty dull. Essentially, all I had to do was make the program click the play button if it was on screen, otherwise click any text boxes that appeared. It was actually a little more complicated than that, but we'll just accept it works. The final, slightly more interesting part of this is detecting when we've completed a level and need to click through to the play button. A solution I found eventually was checking if, after a tile is clicked, a pixel in this region is a specific shade of dark green, which only happens when completing a level. Very handy. And now we come to the main part of the program, solving Voltorb Flip. Sure, we could try training a neural network to work out what's on each tile, but you can't just throw machine learning at every problem, as much as we'd like to. We can instead use a set of logic rules to eliminate possible numbers from each tile until we're left with no choice but to guess the remaining tiles. For example, if a row has a Voltorb total of 0, we can eliminate Voltorb as a possibility from every tile in that row. Now, I could try and develop all the logic myself, but why reinvent the wheel, right? So I found this Voltorb Flip guide on the website The Cave of Dragonflies, which seems to have everything you need to know about solving the game. Using this, I wrote functions for all the rules, which run one after the other to eliminate possible numbers from a 2D array representing the board. I've called this array the memo, as it does the same job as the in-game memo. After all the rules have been applied, we can use the tile clicking function we wrote earlier to uncover all the tiles we're certain aren't Voltorbs, and add the digits on the tiles to the memo, before applying the rules again using the information from the flip tiles. This continues until the memo doesn't change after a full cycle, at which point we've solved the puzzle as far as we can. So at this point we quit out and save our coins, right? Right? Wrong. We start guessing. No, seriously, that's our best option at this point. A lot of the time we'll be wrong and lose coins, but occasionally we'll guess correctly enough times to get to the next level, and this is super important as the number of coins you get increases immensely with each level you get to. Obviously the best tiles to guess have high row and column totals and low Voltorb totals, and we'll want to use modified totals as there's no point guessing in a row with a total of 7 if 2 3s have already been uncovered in that row. As you can see, this works very well. Before we set this running, there's a few optimizations we can make. Firstly, if we know a tile's a 1, then we don't need to turn it over as only 2s and 3s count towards completing the level. On the other hand, if we have to make a guess, then we can turn over 1 tiles until a total of 5 number tiles have been uncovered. Why? When you hit a Voltorb, there's a chance you'll go down a number of levels. The level you go down to is equal to the number of tiles you turned over, up to a maximum of level 5. Obviously, staying at higher levels is important as you get more coins. So, after fully coding an interface to the game and integrating it with a logic-based solver, we can finally put it to the test. I ran the program until 50,000 coins were reached, which is the max amount you can hold, and it took less than 2 hours. This is insane, and I'm really happy with how it turned out. Obviously, yes, this could definitely be considered cheating, but I'm sure you'll agree this was an interesting project, and that's the reason I do stuff like this. Speaking of which, if you've enjoyed this video, you should definitely check out this automated fishing program I made for Stardew Valley, and subscribe so you don't miss anything else.